These are notes on parts of the atom. Just so you know, Mr. Lockett made the transition, so if you don't like them, you can go and complain to him rather than me. So the atom and its fundamental particles. Atom comes from the Greek word meaning indivisible. So the ancient Greeks had this idea that if you took an item, say a piece of paper, you could rip it in half and rip it in half again, and you'd get smaller and smaller pieces, and eventually you'd have a piece of paper that was so small it was almost like the basic building block of that paper. It was so small you couldn't even divide it again. You couldn't cut it or rip it again. And they called that piece atomos, which is Greek for indivisible, cannot be divided. We, of course, now know that the atom is divided into smaller parts, and we call those the fundamental particles. So the first one of those is the proton. It has a positive charge, and it's often abbreviated to P+. The neutron, which is neutral, it has no charge and is often abbreviated to N0. And the electron, which has a negative charge and is abbreviated as E-. And in fact, protons and neutrons can be further subdivided into smaller particles called quarks, and we'll talk briefly about those later, but the main things you need to understand are the proton, the neutron, and the electron. The general structure of the atom is as follows. Somewhere in the center you have a blob, if you will, of protons and neutrons. And these protons and neutrons are the nucleus. You often have you'll hear people say protons are in the nucleus, almost as if the nucleus is a structure by itself, like a car, and protons can be in it or not in it, and the nucleus is still there. The nucleus actually is this jumble of protons and neutrons. And then around the outside of the nucleus, orbiting around, you have these electrons. And I made them smaller specifically so you could see electrons are about 1/2000th the size of the average proton or neutron. You'll often see these electrons on rings. Some of you are still going to use rings in this class. Others of you are going to be able to move on past the rings because the rings are sort of a basic structure, but it does make it easy to draw, and I'll show you why in a second. And we call that area the electron cloud. And the electron cloud, it's not a real cloud, there's no water in it or anything like that, but it's an area where you would likely find an electron, and I'll show you why it's called a cloud in a minute. But then the majority of the atom is empty space. Things between the electrons, well, not even things, there's empty space between electrons, there's empty space between the electrons and the nucleus. The majority of an atom is empty. This is what a picture you might see if you're looking up the electron cloud, and you can see how there's sort of this fuzziness quality about it, which is why it's called a cloud. All of these little dots where it says probability density of electron, those are not electrons. That's where you are most likely to find an electron. So unlike these rings where you'd say there would be an electron on this ring, that's not entirely correct. That is an area where we are more likely to find an electron, but it doesn't mean there's an electron there. I like to use the analogy of a classroom during the school day. It's very likely if you're looking for a student and you look up their schedule that they are going to be in that classroom at that time of the day. But they might not be. They may have gone to get a drink of water, they may have been picked up early for a dentist appointment. It is likely they're there, but there's also a probability that they're somewhere else. So as you get away from this dense region, it's not that there are no electrons there, but the probability decreases. So the relationship between the fundamental particles are as follows. The atomic number is the number of, and feel free to pause the video and kind of quiz yourself on this. And you should have said protons. There are those transitions I was talking about. The mass number is the number of protons plus neutrons. When an atom is neutral, its protons equal its electrons. So hopefully you're starting to see those relationships. So if we have symbol like this, where we have He, that stands for helium, and at this point, if you don't have your periodic table out, you may want to get it out. And then, as you learned in the Build an Atom module, the mass number goes up to the upper left, the atomic number is to the lower left. If there's any charge on the atom, that's to the upper right, and then if there were some sort of subscript, and we'll talk about subscripts later, that goes to the lower right. So, how many protons, neutrons, and electrons does the atom at the left have? Oh goody, we have sound now as well. Hopefully you said that there are protons, 2 protons, because that's the atomic number. Hopefully you said there were 2 neutrons, because 4, the mass number, minus 2, the number of protons, would give us the number of neutrons. And then hopefully you said that there are 2 electrons, in that 2 positives equals 2 negatives. In this case, protons, neutrons, and electrons are all the same number. They're all 2. That's not always the case. There are times when atoms are not neutral, so the electrons and protons won't be equal. And there are times when the number of protons does not equal the number of neutrons. So, using your periodic table, pause after each of these questions, or you can pause right now and write these down. But see if you can figure these out. So the atomic number is the number of protons, and the number of protons determines which element it is. So helium has 2 protons. Its atomic number is 2. If you look on your periodic table, you'll notice number 2 is helium. So who is atomic number 15? You should get phosphorus. How many protons does lithium have? You should see 3. And what is the atomic number of tin? Is 50. Let's look at isotopes, and isotopes are probably new to most of you. Isotopes are 2 of the same element, meaning they have the same number of protons, but with different numbers of neutrons. Isotopes are labeled by adding their mass numbers. So if they have different numbers of neutrons, mass numbers, proton plus neutron, they're going to have different mass numbers. So you add that mass number to the end of the element name. So you would say lithium 6 or lithium 7. And one thing I want to point out is lithium is not capitalized here. You don't need to capitalize names of elements if you're writing out the whole name. If you're just writing the symbol, then we capitalize the first letter. But if you're writing lithium in a sentence, it's not capital. It's not a proper noun. So let's kind of break this down a little. So if we have lithium 6 and lithium 7, let's look at lithium 6 first. Lithium 6, use your periodic table as how many protons? You should have seen 3. Now we know the protons plus neutrons in lithium 6, that's the mass number. That's 6. How do we know it's 6? Because we called it lithium 6. So now you can say the number of neutrons is 3, because 6 minus 3 is 3, or 3 plus 3 is 6. By contrast, lithium 7 also has 3 protons, because it's still lithium. But now the protons plus neutrons, the mass number is 7. And then so the number of neutrons in this case is 4, because 4 plus 3 is 7. So they're both lithium, and they have a lot of properties in common, because they are both lithium. But there are some properties that may be a little different. In general, the number of neutrons determines kind of some specific properties about an atom, like radioactivity. You may find that one isotope of an element is radioactive, but the others aren't. The average atomic mass, which is also called the atomic weight, and that's, if you look on your periodic table, that's the big number with lots of decimals at the bottom of each symbol. That's the average of the masses of the relative amounts of isotopes of an element. So it's like the average of a class, for example. If you were to average out all the test scores, you'd come out with some test score, and that's your average. But the difference is, with test averages, you could have any number of percents. I mean, you could certainly have 100 different percents, but if you said, like, I got an 88.5, I mean, really, it's infinite. Whereas there's only certain isotopes of each element that exist. So let me give you an example. Lithium's atomic mass is 6.94. Now, in the world, there's lithium-6 and lithium-7. There's some other types of lithium as other isotopes, but let's not worry about them right now. Given lithium-6 and lithium-7, which one would you say would be more common? Hopefully you said lithium-7, because 6.94 is a lot closer to 7 than 6 is. So think about it like this. If on a test you could only get 6 points or 7 points, and the average of the class was 7 points, was 6.94 points, then that means a lot of people got 7 and a couple people got 6. Now, this doesn't always hold exactly this way. There are some exceptions where you may have an atomic mass of some number, and in fact, because of the way the isotopes work, say, for example, I think it's chlorine. There's chlorine 35 in the world and chlorine 37, but there is no chlorine 36. So you can't always count exactly on that, but in general, the relationship does hold.